Good morning, and welcome to the ATCO SpaceLab Speaker Series. My name is Kelsey Stephen. I'm a member of ATCO's Transformation Team, and I'm pleased to be your moderator today. I acknowledge the Indigenous peoples that are traditional custodians of the lands that we are on today. While this is a virtual platform, I will take a moment to reflect on the meaning of place, and in doing so recognize the various traditional, ancestral, and unceded lands on which we do our business. I do this to reaffirm my commitment and responsibility in improving relationships between nations and to improving my own understanding of local Indigenous peoples and their cultures. Today's lecture is a one-way video and audio webinar. Please ask questions throughout the session using the Q&A button at the top of your screen, and we will get to these at the end of the lecture. I will now pass it on to my colleague, Andrea Kleiber-Langen, to introduce today's speaker.
Thank you, Kelsey. Welcome, everyone. We're thrilled to have Dr. Peter Vorobieff join us today, an accomplished Regents professor and associate chair with the Department of Mechanical Engineering at the University of New Mexico. Dr. Vorobieff worked in a variety of industry positions before joining the University of New Mexico faculty in 1999. His primary research interests are fundamental hydrodynamics, multi-phase flows, and renewable energy. Today, Dr. Vorobieff will discuss his research on renewable energy. Dr. Vorobieff has pursued projects such as smart buildings with solar thermal power generation for heating and cooling and concentrated solar power systems. In a recent study, he developed and validated diagnostics to quantify the mass and heat losses from the aperture of a falling particle receiver. Dr. Vorobieff will also share information about his involvement in Solar Splash, a national design competition to build a solar electric speedboat. We are honored that you've joined us today, Dr. Vorobieff, and we're excited to learn from you. The floor is yours.
Okay, thank you very much for this introduction. So this also kind of gives the summary of my talk. So ATCO has an impressive portfolio of renewable energy technologies. So hopefully you will find this presentation interesting, because I will be mostly talking about stuff which is not just vanilla photovoltaics. I will start with solar thermal heating and cooling. Then I will talk about solar updraft towers, which is also not photovoltaic technology, and then move on to falling particle receivers and agrivoltaics. And if we have a little bit of extra time, I will also present a couple of slides about Solar Splash. Just out of curiosity, how many people in the audience know what percentage of the energy usage in a typical industrial society is represented by maintaining comfortable temperature in buildings? Turns out that depending on the location, it can be anywhere between 40 and 60% of the total energy usage. A lot, of course, depends on the location. So in Canada, I expect there is more heating, and say in United Arab Emirates, there will be appreciably more cooling and hardly any heating necessary. It would be a very attractive target to apply renewables to, if it were possible for each building to pretty much maintain its own temperature, heat, and cool itself. And again, this doesn't just mean putting solar panels on the roof. It would be kind of nice to construct a smart building that could take care of itself, be self-sufficient. Besides, with heating and cooling, well, you may not even need electricity. So that was the idea behind the design of the building that houses our Department of Mechanical Engineering back when it was designed and commissioned in the early 1980s. But it didn't age well. It had to be retrofitted. Once we retrofitted it, we started tweaking the design and, arrived at some conclusions, uplifting and depressing, which I will share with you in the next probably about 10 minutes. So the current project, or the past project, because right now it's on hiatus, started in the mid-2000s. And the original design had 300 square meters of solar panels, solar thermal panels, on the roof, which generated high temperature thermal medium, which was ethylene glycol water mix, and it could be used directly for heating with a heat exchanger, or it could be used to run a Rankine cycle engine to produce electricity, and cooling of the building was provided by standalone electric chillers. Another interesting feature of that building was that cold water and hot water for heat exchangers could be stored, and there was a huge amount of storage, 512 cubic meters underground. So the other thing that I should have taken picture of but didn't for some reason, the control system for that building. It was state-of-the-art 1980 vintage, so it was completely electro-pneumatic, so just about as diesel punk as it gets. However, the solar collectors that we had on the roof were very high performing from the point of view of optics, but an absolute nightmare when you consider their hydraulics. So the thermal medium circulated through a pipe which was at the focus of a parabolic trough, and all of these pipes were connected in series. So to pump the thermal medium through that panel, you had to use a considerable amount of pumping power. Pretty much to extract a kilowatt, you would need a kilowatt. I'm not being very exact here, but you kind of get the idea. Plus, because it ran at such a high pressure, it leaked like there was no tomorrow. The glycol leaked on the roof and destroyed the roofing material. And in that beautiful electro-pneumatic system, everything that could break did break, and after you replaced it, it broke again. So by the late 1980s, all active energy saving features of the building failed. And by 2005, not only that happened, but also the building was cooled by just one chiller out of original 4 because other 3 croaked. So in 2006, we got some money, interestingly, from the state. And we also found some parts of the original project which never had been installed, specifically legacy flat plate arrays. We also decided to install these arrays and buy some new solar thermal modules, vacuum tube, which produces a much higher performance. We decided to insulate our storage tanks so that there are fewer heat losses from storing cold and hot water. And we decided that we're not going to run the Rankine cycle engine, but instead we will use a lithium bromide absorption chiller to generate cold water. In other words, our design would be consistently thermal from the roof to the chiller in the basement. That's 26 meters elevation difference. Plus, of course, everything would be on direct digital control, variable frequency drives on everything that rotates and has some kind of a rotational frequency. And then, of course, we also wanted our system not to share the fate of its predecessor, so it would be designed with fail-safes and redundancy. More on that later. So this is how the legacy flat plate array looks like, and it was made by an American company, Lennox, which is still in business but no longer produces solar thermal panels. And this is the new vacuum tube array, which is assembled from individual vacuum tubes that feed into the same header. And supposedly the performance of this design is higher than the double glazed flat plate array I showed to you in the previous slide. And this is a view of one of the storage tanks from the inside, showing the process of installation of the insulating materials. And these tanks are huge. So there are 8 of them, and they are 4 by 4 by 4 meters. So what we found after the design was implemented. In Albuquerque, New Mexico, unsurprisingly, the peak load is not heating, it is cooling in the summer, and we cannot run the chiller on the hot water from the panels that we store. It runs out. So we decided to do an upgrade to this redesign, trying to minimize energy losses, tweak a few things about the instrumentation and controls, but most importantly, remediate that deficiency of the chiller performance by installing booster mirrors. And a while ago, we actually wrote a paper which was titled Poor Man's Concentrating Solar Power. This is what booster mirrors are. Let me also mention that we found a wonderful way to cheat using the peculiarity of how the local energy company works, PNM. So they have a very low tariff for electricity at night. Correspondingly, what we could do is we could run electric chillers for the water in the physical plant building, which is not very far from ours, store that water in our storage tanks, and then utilize it during the day. And this way, the savings from using that cheaply generated chilled water added up with the savings already produced by the system as installed. And that actually amounted to a significant chunk of change. Now, let me switch to the booster mirrors. We wanted to catch the morning sun and improve the performance in the morning hours. We wanted the setup to be cheap and lasting, and we didn't want to change the arrangements of our already installed solar thermal panels on the roof. And we also didn't want to boost the peak power around midday because the components of the system just wouldn't be able to handle it. So what we decided to do is just use the space between the rows of our panels and put some booster mirrors there. And the design underwent an optimization study in terms of angles alpha and beta, which are shown in the pictures on the right. And we came up with values for both the legacy panels and for the vacuum tube panels. And that study was done by simulating the conditions in Albuquerque, the trajectory of the sun, and the geometry of the panels and the mirrors with public domain ray tracing software. This is how a row of booster mirrors actually looks like. And here it's what architects use the word vernacular materials for. So the only high-tech component here is aluminum film with some plastic coating, which was guaranteed for, I think, 15 years, but the company since ran out of business. And it is backed by an aluminum sheet from a hardware store, and the frames are wood from the same hardware store. These are very similar in design booster mirrors facing the vacuum tube arrays, and as you can see, they are oriented to redirect the morning sun, which comes from the east, onto the arrays which are facing south. So with the redesign, the components of our system include the flat plate and the vacuum tube arrays with booster mirrors. There is a cooling tower that dumps waste heat from the lithium bromide absorption chiller. And now with this design, what we can do is we can just use our chilled water from the chilled water tanks to cool the building. And in the winter, use hot water tanks instead. So the vacuum tubes, despite their very simple setup for the boost with mirrors, show an appreciable performance boost. And if you look at the comparison of the boosts, there are two configurations, at one of the angles being 20 degrees and 30 degrees. So you guys can see my cursor, yes? Both of these configurations significantly outperform the unaugmented vacuum tube array. Now, the peaks here are for the time when the absorption chiller kicks in. Before that time in the morning, there are some fluctuations during the startup time, and at the time between 10 and approximately 11:45, the cooling system runs on chilled water stored from the previous night. So the mirror cost was within the specs of what we had allowed ourselves to spend, less than 5% of the total system cost, but it produces a peak energy collection increase of about 40%, and the average daily increase, interestingly enough, on a sunny day was 20%, and on a cloudy day, 35%. Go figure. So with that boost, the runtime of the absorption chiller also increased by something between 20 and 35%. And this is for handmade custom booster mirrors. Were you to install such a setup on an industrial scale, the costs would be further lowered. So all is well, you will say. Not quite. And this is one of the reasons why solar-driven or solar-assisted building heating and cooling is still not mainstream, even though you can implement it and you can enhance it with booster mirrors for a very small fraction of the overall system price. But no matter how many fail-safes we installed in our system, unfortunately, nature always comes with a higher grade of fool to override your fail-safes. We never imagined that some genius decided to save $500 on maintenance and not put in the treatment for the solar thermal medium, which was a mixture of propylene glycol and water. As the consequence of that, the main pipe between the absorption chiller on the bottom and the array on the roof corroded beyond repair. And since that pipe was a part of the original setup of the building, it was inside a concrete slab, so it just pretty much rusted to the point where the thermal medium could not go through anymore, and the system is no longer operational. The physical plant people who are responsible for this screw-up kept promising that they would fix it, but, well, that happened in 2016, and I'm not exactly waiting for them to come and fix it with bated breath. So the Achilles heel of all solar thermal systems to assist or to provide building thermal conditioning is just that they need people who know what they do when they maintain these systems. I will provide, if you email me, a PDF of this talk, and you can peruse some of the papers that our team wrote. So that project was co-led by me and Professor Andrea Mamoli, who now works at Sandia National Labs, and he's mostly doing grid optimization these days. Now, these are some foxes from Scotland. And with these foxes, who once upon a time decided just to show up in some professor's backyard and self-domesticate, let me switch to the next subject of my presentation, namely solar chimneys. Again, we are in the territory of solar thermal energy generation, and the idea itself is ridiculously simple. Let's say you have some land in some sunny place, and you build a big, flat, transparent roof over that land. And then you poke a hole in the middle of that roof. You install a chimney above that hole, and you somehow put turbines inside the chimney, and then buoyancy will drive flow through the chimney and generate electricity. Importantly, if your setup is big enough, the ground under the roof will heat up, and for a sufficiently large facility, the turbine will turn over 24 hours per day, so it could be a baseline source of renewable energy, not subject to the sun rising and setting. Furthermore, you could boost the thermal storage by adding some kind of thermal media under that roof, like, for example, bladders with water. You could use the same greenhouse to grow vegetables, for example. So lots of interesting possibilities exist. The only problem is that for this setup to be competitive with other ways of generating electricity, it has to be ridiculously huge. Like the chimney has to be 1 kilometer tall. I put the Burj Khalifa building in this slide just for comparison. So the advantages of this idea is that you can really have yourself a baseline power production using renewable energy. The components are really simple and don't require much maintenance. You can build it in the desert, and conceivably, even though it is pretty large, you could build it cheap. There was, to the best of my knowledge at the present point, only one real prototype facility built in the 1980s in Spain by a German engineer, Jörg Schleich, and it was supposed to be a scaled down version of the full-size power plant. The tower was about 200 meters tall. The collector area was half a square kilometer. The depressing part is the power output. Huge facility, 36 kilowatts. Plus, the tower was built of metal, the thinnest they could find, held by guy wires, one of which rotted through, and in 1989 that whole thing fell and crushed its own greenhouse. So it only lasted for about 7 years. There are some other solar chimney projects, but to the best of my understanding, none of them are operational. So there was supposed to be some construction in China, but nobody really knows anything about that. There was a project which was discontinued before the preliminary build stage in Spain in 2009. The same fate befell an analogous project in Namibia. In Australia, and then the company that collected money to do a feasibility study in Australia moved to Arizona, collected more money there, still no solar towers. Why such a, I wouldn't say spotty history, because this history is pretty much one big spot, nothing bright about it. There are several reasons. Huge upfront costs, most of which is building that kilometer-tall tower, difficulty of construction of the same tower, and vulnerability of that tower, once you build it, to weather and seismic events. So something might have to do with that whole concept of a 1 kilometer tall tower thing, especially if you build it out of concrete. So why not replace the concrete tower with a stack of inflatable toroidal bladders? That would colossally cut the costs of construction. Plus, our original idea, and here by we, I mostly mean yours truly, and the brain behind that project, I would say mostly provide the brawn. The brain behind that project is a person some of you probably know because he worked at ATCO for quite a while, Professor Vakhtang Putkaradze. So the original idea was to maybe even put helium in these toroidal bladders, because in that case we wouldn't have to worry that much about the weight of the construction. We would have to worry about it flying away. Now, Vakhtang came up with a really simple theory describing the behavior, the desired behavior of such a stack of bladders. His idea is that in the wind, you can allow that stack to bend, but you don't want it to flop around or to behave like a streamer that they sometimes put in front of car dealerships and whatnot. And most importantly, you don't want it to kink. You want it to provide uninterrupted airflow. So his idea was that you could look at the bend angle of each torus with respect to its neighboring tori, and you could approximate the compression in each torus by looking at a crescent shape indentation that the tori produce between each other when they are compressed on one side. This leads to a relatively simple geometrical interpretation of the change in the volume due to the wind force and correspondingly of the pressure force that balances the wind force. So in theory, the balance of these two forces, the wind loading and the compression, should generate a known torque acting on each of the tori in the stack. The equilibrium condition is that the wind loading is balanced by the compression due to the deformation, and this produces a system of coupled nonlinear finite difference equations for angles between the tori. So what you can do once you have set up these equations is you could look at different shapes of the tower, which would help it withstand the wind loading the best. And we originally tried two designs. One case is when the inner radius of the tube is kept constant, and the radius of this donut is the only component that we optimize. And in the other approach, we say that the ratio of the radii of the tori is constant, so a larger torus will also have the larger tube diameter, and the smaller one would have a smaller tube diameter. So these designs we refer to as explicit and implicit. And then we tried to take these finite difference equations and determine the optimal shape of the tower, which would be able to withstand the highest wind loading with the least overall bending. The results for the explicit and implicit shape that were modeled and published are shown here, and as you can see here, the explicit tower, it's a tower, but it's not much of a chimney because it shrinks from 200 meters at the bottom to 10 meters at the top. This will not work. On the other hand, the implicit design looks much better. After we did that, we did some numerical modeling, and since we didn't have to build the actual tower, we also decided to play fast and loose with the specs of the system. We decided to see what happens if we pop our turbine on the bottom of the tower, or if we pop it on the top of the tower. Also ran a reference case without the turbine and the associated pressure drop. And the results for the performance of such a facility, and here we are looking at a 750 foot, not foot, sorry, no feet here, only metric system, 750 meter tall tower for the straight section of the chimney where it wouldn't narrow on approach to the top. The best configuration would be if you have the turbine at the bottom, and in this case you would be getting about 60 megawatts from this facility, whereas if you went with the implicit design, which would withstand the wind loading the best, your output would drop because your cross section would be narrowing toward the top, but it wouldn't be dropping really that much. You would be getting 50 megawatts instead of 60 megawatts. So I would say this is probably the acceptable price to pay for the advantages offered by this design. It's about 15%, but the inflatable tower, we ran an estimation and we even called some companies to build as a prototype. Instead of hundreds of $millions, you could get away with spending single millions of dollars, plus inflatable towers can be deflated for maintenance, hidden away in case of extreme weather, and whatnot. We also decided as a student project to build a small-scale prototype using the implicit shape, or as close as we could get to it, by sourcing inner tubes from bicycle, motorcycle, and scooter tires. And the height of that tube was 4 meters. And it produces about 20 watts of power with a little portable wind generator that was put at the bottom, wind turbine generator, I should say, put at the bottom of the tower. And everything else is, again, pretty much vernacular. Plastic film, inner tubes, as I said. The most interesting thing about this design, though, was how well it withstood winds. And we were lucky enough that during the testing by the student team, there was a hurricane strength wind blowing through Albuquerque, which completely tore out all the plastic film, but the tower still stood. Even more interestingly, since we had data from the wind speed during that event, we could do a comparison of theory versus experiment in terms of how much that tower deformed for different wind speeds. And theory and experiments pretty much agreed, except for the very top portion of the tower, where we couldn't find the right size inner tubes. So, Professor Putkaradze and yours truly and some of our colleagues further looked at optimizing this behavior of this inflatable tower in real time. And there are certain strategies for that. Plus, you could also use something that already generates heat, like, for example, a landfill, and pop a solar chimney with a roof over that. Or even more ambitiously, you could use a solar chimney to dissipate heat from, say, a nuclear power plant. Again, we published some papers, and we also got some patents both for the geometrical aspects of the design and for its ability to accommodate solar power generation and use of waste heat from a variety of sources. That's just a puppy. And this moves me to the next subject. Still no traditional solar panels. Instead, imagine a giant field of heliostats, all sending the sunlight, reflecting it to a single spot on a tall tower, not quite as tall as you would need for a solar chimney. The tower in the photograph is about 90 meters tall, I think. And what happens then is you have yourself a spot of highly concentrated sunlight, up to 1,000 suns. And with that sunlight, you can heat up some thermal medium, which you then can store and use it to run some sort of heat engine cycle. People use Brayton cycle frequently, but if you have enough of such medium stored, you can run that cycle 24 hours per day. So again, the goal here is baseline production of energy, not something intermittent. The problem is thermodynamic efficiency. Many of you may have heard about the giant facility of this type, Ivanpah plant, which recently shut down. They used water as their thermal medium. And if I remember correctly, it was just steam turbine generation of electricity. The higher the temperature of your thermal medium, the higher the limit on the performance of your system. And, well, water just don't cut it. Molten salts are slightly better because you can heat them up to a couple hundred degrees centigrade. But what would be even better is ceramic particles, which you could very easily heat above 1,000 degrees centigrade. And the goal here as said by the US Department of Energy, is to develop prototypes that could be industrialized and provide energy at levelized energy cost, which makes this design not just competitive, but which makes it outcompete other available designs. The problem with particles, you have this highly concentrated sunbeam on them, and usually particle receivers run with an open aperture. So you just have a curtain of particles falling down, being heated by this ultra-concentrated sun. And also, if you look at it from the side, the particles do all kinds of nasty things, like they get blown off, fall on the ground next to the tower. You have obviously mass and thermal losses in your thermal medium, the particles. So how bad does the situation really get? We decided to build our own tightly controlled laboratory conditions miniaturized version of the Sandia solar tower. So that instead of getting 1,000 suns in a spot of about 1 meter by 1 meter, we would get it in a spot 10 by 10 centimeters. And we used solar spectrum light bulbs with reflectors to generate roughly 1,000 suns. And then we preheated our particles in a tube furnace and poured them to create a curtain that was very similar to the curtain that was used at Sandia, except much smaller. And the most important part is, what we wanted to do is we wanted to collect as much information about what is happening with this particle curtain as possible. And to do that, we used two ranges for imaging the curtain: the infrared range and the visible light range. So we had a combination of a high-speed infrared camera and more or less a conventional SLR digital camera. So this is what the results look like, and the thermogram and the visible light image sequences are time resolved, and with the thermograms we were able to get up to 300 frames per second. And the reason why we needed such detailed diagnostics was that we wanted to be able to use just images to determine the particle temperature in a way that could be used when we run experiments at the full-scale Sandia facility. Why is this more tricky than it could seem? After all, you've got the thermogram. The problem with the thermogram is that each pixel in the thermogram is a combination of particle temperatures and the background behind them. So there are a couple of other variables, such as the thickness of the curtain, resulting in its overall opacity, emissivities of all the components. So mercifully, all of this has analytical or semi-analytical representations. And one of our students, Jesus Ortega, came up with a particle temperature reconstruction algorithm, which was then validated using our laboratory data. And after that, we also were able to extract not just the temperature, but the velocity field overall and for, excuse me, individual particles. So if you have a thermal map of what's going on and a velocity field of what's going on, you can scale this up and assess both the mass loss and the thermal loss from the full-scale receiver. Now, these are some of the results from the experiments in the full-scale setup. We had to protect our cameras from the elements and from the particles themselves, but then we popped that setup on that tall concrete tower, and you can see, I think, the people on the bottom of the right image are Dr. Ho from Sandia and Jesus, who was at the time not a doctor yet, now he is. And after that, we collected some thermograms. They required some considerable post-processing to extract the information that we need to reconstruct the velocity fields. But after this was done, we were able to measure both the heat loss from the particles and the particle egress rate, so the mass loss rate. And this facility, in its configuration as tested, produced about 71 kilowatt. The input power averaged during the time of our tests 420 kilowatts, but accounting for advective losses, the receiver efficiency was better than 80%, and these advective losses accounted for about 70% of the total losses in the system. As the consequence of that, we got the green light to go ahead with the next stage of falling particle receiver work, which is something that we are working on right now. And for a commercial scale receiver, the target size of the area which will be used to collect energy is 100 times what we previously worked with. So, first of all, flux over such an area can no longer be uniform, and one of my students is currently working on modeling that flux. Plus, also to account for these non-uniformities, you need more particles falling through the areas where the concentrated power is higher, and fewer particles falling over areas where it is lower. So you cannot have a single curtain. You have to control the flow rate individually in various segments of that curtain. And right now, the system that we envision has 10 such segments. Again, here are the references for the papers. Now let me switch to some cute new projects. One of them is agrivoltaics. And the idea here is pretty simple. I already mentioned using the same real estate to generate solar power and possibly to grow some plants under it. So conceivably, what you would do is you would build a greenhouse, then you would put some solar panels on top of the sheets that form the roof of that greenhouse so that the inside of the greenhouse is partially shaded. We put that on the roof just for a change, not our department, but on the roof of the biology department. And we grew lettuce, tomatoes, and strawberry over the last summer. And the surprising result was that for most configurations of the shading elements, crop performance was actually improved by the shading. The sun in New Mexico is harsh. Buoyed by these results, we are now proceeding with a larger scale installation on the Rio Grande Community Farm, and hopefully we will get some results from how well that facility performs in the summer of 2025. I did say hopefully, didn't I? Because I just don't know in the current political climate. Now, do I still have a few minutes?
Yes, we still have about 10 minutes.
All right. So let me just quickly run through the solar splash slides, and this time there will be photovoltaic panels. So it's a design and build competition, which is international. It is run in the United States and in Europe. And the idea is to build a solar-powered speedboat and to race it. So you are allowed up to 720 watts of solar panels, no more than 45.5 kilos of batteries, which also have to be lead acid, so the components are cheap. Bunch of other rules, but let me just dispense with that and show you what it looks like. There are 3 events. One event is going very fast in a straight line. The other event is going around buoys very fast. And the third event is going around the course for 4 hours straight. And whoever makes the most laps during these 4 hours wins. So you have to optimize your boat both for performance and for endurance. This is our 2024 boat, and right now it's moving at its cruising speed. So during the competition, you are not allowed to use any other source to charge your batteries than the sun available at the competition venue. This year it was, last year it was in Ohio. And as you can see, our boat is carbon fiber. Very lightweight, and its cruising speed during the endurance event is about 4 knots, but its speed during the high speed events is closer to 20 knots. Let me show you some more videos. So that's from the 2022 event, and as you can see here, the basic setup is similar, but this hull was built of marine-grade plywood, not carbon fiber, so that boat was a bit heavier. But as you can see, it can go pretty fast. And it steers reasonably well too. Although this year my kids want to do a different system of steering, well, we'll see how that goes. And this is from an early year, and this is one of them go very fast in a straight line events, also conducted in the rain, just to make the challenge higher. And this is how fast these boats can go. Again, it's something to the tune of 20 knots, or maybe even a bit faster than that. And there were 3 boats on the course, but you can only see ours because the other 2 are left far behind. So with this, I think I can conclude my presentation and answer any questions from the audience.
Great. Thank you very much, Dr. Vorobieff. For everyone who joined us online, please send your questions to the Q&A button at the top of your screen, and you can upvote any questions that you'd like me to answer. I'll try to get to as many as I can in the time that we have today.
Okay, so Kelsey, you will read out the questions, yes?
Yes, I will.
What, no questions? Let me open
We'll give
up the
everyone a few
Q&A.
seconds. I'm sure people are typing.
Yeah, so no questions can mean 3 things. 1, everything was crystal clear. 2, everything was incomprehensible. And 3, the speaker put everybody to sleep.
Okay, we've got questions coming in now. Our first question is from Patrick. Patrick asks, for the solar chimneys, are there any natural structures you could take advantage of to save on cost?
This was considered, And one of the ideas, and actually a really old idea, I remember that I think it came with some civil engineer either in Spain or with Portugal sometime in the beginning of the 20th century. Instead of having a freestanding chimney, position it on the slope of a hill. So yes, this has been considered, and this is distinctly viable.
Great, thank you. Our next question comes from Mary, who asks, what would you think of putting little turbines at the top of roof ridge?
As a matter of fact, something like this already is commercially available, and they are called solar chimneys. The reason for them is completely different, though. These are not used to generate energy. They would be able to generate a puny amount, but they make a huge difference in the temperature in your attic. And as the consequence of that, they help you cool your house, if it has an attic, way more efficiently. This, by the way, brings me up to one important point that I forgot to make because it's kind of outside the scope of the work I presented today, but still very important. Before you start considering active measures to create a green building, such as photovoltaic or solar thermal panels, absorption chillers, whatnot, first you have to make sure that your building is optimized using passive measures. All the doors close well, there are no drafts. All the windows are double glazed. Wall insulation has a high R factor, and so on. And these are not nearly as dramatic or as expensive as active measures, but they lead to significant savings on energy, especially for older buildings.
Great, thank you so much. While we're waiting for some more questions, I was going to ask you a question.
Yes,
I'm
please.
very interested in the solar splash, and I was wondering if you tried to apply some of those same concepts to bigger boats, would it work the same, or would you have to make a whole bunch of changes?
Well, I didn't. Other people did. There exists a solar-powered electric boat which circumnavigated the world. It is called Turanor. And it is also a very interesting exercise in hull design. So they have a very low drag hull configuration. So it is entirely possible to circumnavigate the world using solar power. Also, there exists, I don't remember the name of that boat, but it is used to transport Toyotas from Japan to the United States and Canada. And this is a commercial boat with a diesel engine, obviously, but it also has solar panels installed on it. And some people would call it greenwashing because these solar panels only provide a very small fraction of the overall power capacity of the boat. The boat cannot run on them, but there is an important aspect that was looked at a faculty member from, if I remember correctly, University of Ancona in Italy, yes, Giorgio Paserini, which nearly cost him his life. So he decided to measure emissions from various commercial ships in the harbor of Ancona. And some crew members took offense to that. But anyway, his conclusions were that during the time the ship is in port, there are some power hookups, not enough for all the ships. So they pretty much run their diesels or some sort of onboard generators on idle, and they use some absolutely cheapest, dirtiest diesel fuel. And when in harbor, these guys pollute like there is no tomorrow. So if you have an onboard capacity to generate your electricity, this pollution problem goes away, and all the people living in all the port towns across the world would be much more happy.
Very interesting. Thank you so much, Dr. Vorobieff. We have another question from Mary. Have you considered collecting rainwater off the solar panels? I was thinking it could be used to water the plants or fish tanks below.
Well, in the case of our greenhouses, the rainwater collection is sort of automagical. So the runoff from the panels is just redirected to the plants. But to be absolutely honest, New Mexico, summer, rain. What's rain? Well, just kidding. We have a monsoon season. So yes, that's a part of our design.
Thank you so much.
The only problem is if you only use rainwater, and again, I'm talking New Mexico, not say Alberta. There are very few plants that will grow and thrive only using the precipitation that is naturally available. So you will need to boost that with some external source of water. Although the plants that grow in our arid climate often have interesting medicinal properties. I'll leave it at that.
Perfect. Thank you so much. We have another question from Patrick as well. In Alberta, we have significant heating and cooling requirements based on the time of year. How would such a solar thermal heating and cooling system have to differ from the one you described at UNM?
To tell you the truth, not by much. You would have to tilt your panels at a sharper angle. Typically, the tilt angle should be equal to your latitude. So that would be different in Alberta and in New Mexico. But in terms of having to deal with both heating and cooling, well, we have a winter with snow, and we have a hot summer. So from my understanding, Edmonton, for example, has a rather stereotypical continental climate. So the winters are cold, the summers can get hot. So you would have to meet both the heating and the cooling load, except that in New Mexico, the winter would be shorter and the summer would be longer. But the facility would have to be designed using a very similar setup and similar components.
Thank you so much. We have a question from Stefan who asks, for the solar splash, are you using any energy recovery systems?
Not at present, and I'm not sure if it is allowed by the rules. The goal here is to keep things as simple as you can humanly make them. So you have a hull. Inside the hull, you have an electric motor that drives a prop. The motor, in turn, is driven by a controller. The controller is powered by a battery stack. The battery stack is connected to a multiple power point tracker, which in turn is connected to the solar panels. And that's it.
Great, thank you. We have another question from Mary. Have you heard about the cloud study which indicated the ship pollution contributed to more cloud production?
That's applicable both to ship diesel engines and to ground-based. diesel engines because what they produce is not just greenhouse gases, but soot. And also all kinds of chemical stuff that I am not really well versed in. Nitrous oxides. And as the result of these factors, diesel exhaust can indeed leads to not just heating of the atmosphere, but also cooling of the atmosphere as well, both by, soot and other things. They create little centers around which droplets can form, and that can lead to cloud cover. And during the COVID pandemic, when international shipping was affected as well, there even was a measured effect of that on the weather.
Thank you very much. At the moment, we don't have any other questions, so I'll give the audience about 10 seconds just to make sure that nobody's kind of straggling behind.
Okay, and if there is any interest in follow-up to my presentation, I will send a copy of my slides without the videos to Kelsey, and you can also email me directly.
That sounds wonderful. Thank you.
Okay, that's it then.
Yeah, it looks like,
Well,
yeah,
all
okay. It
right.
looks like no other questions have come in, so that will be the end of the lecture today. Thank you for joining us, Dr. Vorobieff.
Thank
We
you
really
very
enjoyed
much for
learning from you
inviting me.
today.
Thank you very much.
And thank you everyone who joined us online. It was really great to see some familiar faces joining us again. And please stay tuned for our next lecture and enjoy the rest of your day.